Okay, so here's our question. We've got three equations and we want to find P and Q such that there is no solution or that there are infinitely many solutions. So the first thing we need to do is write these equations in a matrix form. Now we find the determinant of the square matrix on the left-hand side. So the determinant has been found to be 2 minus 4p. And for both of these cases, we want it to equal 0. In the context of having three equations, we should consider what is meant by having no solution or infinitely many solutions. It's easy to see that the determinant is going to be 0 when p equals a half. For the case of no solutions, we could have that all three lines are parallel. We could have that they all intersect with each other but at different places. Or we could have that two of them intersect and one of them doesn't. Or because we're working in 3 dimensions, we could even have it that all three lines are just in different planes, and so they never run into each other. For the case of infinitely many solutions, it's still the same old, all three equations represent the same line. And so you get infinitely many points of intersection. So returning to the question at hand, here's our system of matrices that we had before, but this time all I've done is subbed in P equals a half. In the case of having infinitely many solutions, we want to show that one of these equations is made up of the other two equations. And to do this, we do something called row reduction, which is actually quite easy. All it is adding and subtracting rows from each other. But it does take a little bit of guesswork to get where you want to go. And basically, row reduction has two rules. You can multiply any row by a scalar number, and you can add and subtract any row from any other row. So let's give this a go. Here's the same matrix as before. This time I'm going to multiply row 2 by 2 to get rid of the fraction, just to make it easier to look at. And you can see that I haven't multiplied the second row in the x, y, z column matrix, but I have multiplied the second row on the right hand side of that other column matrix. So instead of being 1 negative 4q, it's now 1 negative 8q. And because we only multiplied row 2 by 2, row 1 and row 3 have stayed the same. And now we are going to subtract our new row 2 from row 1. And we don't do anything with row 2 or row 3, we're just making a new row 1 by taking old row 1 and subtracting our row 2 from that row 1. Okay, and this is the result. You can see that row 1 looks a lot like row 3, except over the right hand side where we've got 9 minus 8q, you can see that q and 9 aren't quite the same thing. But what could we make q so that row 1 matches row 3 exactly? I think it's just a coincidence that 9 looks a lot like q. And the answer is that q equals 9. So we can write down what we did in terms of our original rows as the following. We showed that row 3 is equal to row 1 minus 2 lots of row 2. And this is the case when q equals 9. So we've basically finished this question. Let's have a look at each case. What do we need so that we have infinitely many solutions? We want the determinant to be 0, so we have p equal to a half. And we want that one of the equations is a linear combination of the other two equations. And in this case, that happened when q was equal to 9. And for this particular question, the linear combination was that row 3 is equal to row 1 minus 2 lots of row 2, or that equation 3 is equal to equation 1 minus 2 lots of equation 2. How about in the case of no solution? Again, the determinant needs to be 0, so p is equal to a half. But in this case, we don't want one of the equations to be a linear combination of the other equations. So we don't want q to equal 9. So for any q that's not equal to 9, you won't get this linear combination stuff where one equation is actually made of the other two equations. And now, while it's not in the question, what would the condition be for a unique solution? The determinant shouldn't be 0 for a unique solution, so that means that p can be anything that's not a half, and q can be any real number. And that is the question done and dusted.